Hi everybody, we are working with basic chemistry, and if you're following me in the course pack, let's start on page 19. This information will carry you on to page 27 of the course pack. Now, this is a pretty hefty topic, and I do recommend flashcards if you're having trouble remembering some of the important components here. For instance, for each organic compound group, you may want to make flashcards on the name of the group, the building block or monomer, any special examples, the function of the group. Okay, and so you'll want to make sure you put that on flashcards and review that until you can get this stuff to start to stick. It's dry information, and it does require a little bit of review to help get this stuff to commit to memory. So organic compounds are compounds that are typically containing elements like carbon, hydrogen, and oxygen, and also sometimes nitrogen, phosphorus, and sulfur. The carbons and hydrogens may exist in long chains, and I'll show you an example of that in just a moment. While organic compounds may be produced by living organisms, that is not a requirement to be an organic compound. These organic compounds are often created from covalent bonds and exist as macromolecules. This is a great time to review. What are covalent bonds? Well, they result from the sharing of pairs of electrons. And so you're going to find single, double, and sometimes triple covalent bonds in the images that we see as we work through this content. Here's a good way to review as well. In a previous topic, we talked about catabolic reactions which break down macromolecules into their building blocks. And we also talked about anabolic reactions which build building blocks into macromolecules. So when we talk about organic compounds, we are talking about how to reassemble the foods that you eat into the components that build our bodies. There's also a piece of the puzzle here. The carbohydrates can provide energy, and if necessary, fats and proteins can as well, but the most direct route to producing ATP energy is by breaking down a carbohydrate known as glucose. So when you're thinking about these organic molecules, think about the big picture. What you eat ends up building your body. Also, when you look at food labels, you may notice things like lipids on there. They're labeled as fats, cholesterol. We also see carbohydrates, which give us quick energy. And we also see proteins. So there's a lot to learn from looking at a food label, and what we talk about today will help you understand better what you can actually see on a food label like this one here. So let's start with the carbohydrates group. First of all, you'll notice the word carbohydrate has some information hidden in it. Carbo is carbon. Okay, so that prefix right there, that is carbon. Hydrate actually means water. That's H2O. Okay, so right off the bat, you can see the ratio for carbons, hydrogens, and oxygens is in this format. Twice as many hydrogens as carbons and oxygens. So you may find a common compound like this one. Okay, and in that compound we see twice the number of hydrogens as carbons and oxygens, so it more or less fits the bill of being a carbohydrate. So right here we can see the ingredients for fuel: carbons, hydrogens, and oxygens. In fact, the building block or monomer for this group is called the monosaccharide. Let's break that word down. Mono means what? One. And what does saccharide mean? Literally one sugar. So this particular group helps to give us energy. The quickest way to get energy is from the monosaccharides because they are our simple sugars. Disaccharides are also simple sugars, however, they're composed of two, that prefix di there, two sugars. Polysaccharides give us the most long burn of energy. In other words, if you're going out for a run and you want to have energy to last you the entire time, then a polysaccharide is your best bet because it contains many sugar molecules joined end on end. So from the mono down to the polysaccharides, the mono give us the quickest burst of energy, and the polysaccharides give us the longest burn of energy. So let me put it to you this way. If you're going to build a fire and you want a quick hot fire that burns out quickly, pick a monosaccharide. However, if you want to have a fire that lasts you all night long, a long burning fire, in other words, long burning energy, pick one of those polysaccharides. Monosaccharides typically have between 3 and 7 carbon atoms. So taking a look at glucose here, it is arranged in a ring structure, which is typical for many of our organic compounds. You may recall these single lines here are single covalent bonds. And you may recall that this set of double lines here is a double covalent bond. You're also looking at carbon atoms. They've numbered them for us. I'm going to circle them. There are 6 carbon atoms here. That means that this does qualify as a monosaccharide because monosaccharides have between 3 and 7 carbon atoms. Glucose, by the way, is your body's preferred fuel for making ATP, and you may recall from an earlier biology course that this occurs in the mitochondria. Okay, so glucose is the building block for many of our molecules here, and in fact it does qualify as a simple sugar. You can see on the left, that is the linear form of glucose. All we've done is taken that particular set of bonds and we're arranged it in a ring structure. So what you see on the right is in fact the same numbers of carbons, hydrogens, and oxygen as you see on the left. It's just that we've arranged it in a ring form for glucose. These are isomers of glucose. Glucose has the formula C6H12O6. Now, these all qualify as monosaccharides because they have between 3 and 7 carbon atoms. Also, they qualify as carbs because they have twice the number of hydrogens as the number of carbons and oxygens. If you take this formula up here and boil it down to its basics, you basically have CH2O. Now, glucose is pictured on the left. Galactose, its isomer, is pictured on the right. You will notice the only difference is shown here in red, and that is this set of hydrogens and oxygens that are bound on the left side of the molecule. They are flip-flop from what you see over here on glucose. Now, your body can tell the difference. It prefers glucose for making ATP. However, galactose is very similar because it has the same chemical formula. So let's come up with a definition for isomer. We already know that iso means same. So what they have is the same chemical formula, C6H12O6. How do they differ? They differ by having a different chemical structure. You can see where those hydrogens and oxygen are located. This is also a good time for me to mention this, the OSE ending that you can see here. That OSE ending is a great reminder that we have a sugar. Most of our sugars will have that OSE ending. Now, OSE does not tell you if it's a monosaccharide, disaccharide, or polysaccharide. The only thing it tells you is this chemical compound is a sugar. Here is fructose. It is also an isomer of glucose. So what does that mean? What does it share with glucose? Well, they have the same chemical formula, right? C6H12O6. How do glucose and fructose differ? By their structures, right? So take a look. We actually have a 6-sided ring over here on glucose. I'm just going to draw over that 6-sided ring. And here for fructose, we have a 5-sided ring. Okay, so your body does know the difference between glucose and fructose. That's why there's a lot of conversation about high fructose corn syrup and if it provides the same benefit to your body as does glucose. We think the body does know the difference between these two molecules, even though they have the same chemical formula. So here's glucose, galactose, and fructose. It makes it pretty obvious that they have different chemical structures, but they all have the same chemical formula, which is C6H12O6. So that's why these three are all isomers of one another. Let's talk about disaccharides for just a moment. You'll notice here that glucose and glucose can join together. We are dehydrating or removing the water molecule right there, and that allows us to join together the two glucose molecules to make maltose. So maltose is in fact a disaccharide. Okay, so maltose is a disaccharide, meaning it's made up of two monosaccharides. If you'll take a look at this formula up here on the top, you'll notice that glucose and glucose added together yield water and maltose. This is a great example of a dehydration synthesis reaction. And the reason I know that is because I have two monosaccharides joining together to form a disaccharide, and water is also a product over there. So what is the other name for a dehydration synthesis reaction? It's also called an anabolic or a building reaction. You'll also want to know sucrose as an example of a disaccharide. It is, however, made up of glucose and fructose. So again, these same chemical formulas join together and creates a sucrose molecule. You'll notice once again we have a dehydration synthesis reaction down here at the very bottom, also known as an anabolic reaction. So glucose is a monosaccharide, that's one. Fructose is a monosaccharide. Sucrose is a disaccharide, and of course water is dehydrated away from glucose and fructose, and so therefore we show it as a product. Just another view of maltose here. You can see two rings of glucose joined together. Let's now talk about polysaccharides. So polysaccharides give you the longest burn of energy because they are made oftentimes of many, many molecules joined together. The one you're looking at here is called glycogen, and you'll notice it has many rings of glucose. Each one of these individual rings is a glucose molecule. So, boy, that's a lot of carbons, hydrogens, and oxygens that you have to burn in order to break down a glycogen molecule. Now, you store glycogen in two main places, in your muscles and where else? And your liver. Okay, and you don't store them in your muscles for very long or your liver for very long, about 2 to 3 days. After that period of time, your body says, hey, let's turn this into fat. So after 2 to 3 days of storing glycogen, you will store that as fat in your adipose tissues, and that's under your skin and around your organs. So glycogen is a temporary storage supply of excess glucose. Let's also talk about insulin. Insulin is a hormone that's made by your pancreas in response to high blood sugar levels. When you've had a dozen donuts from Krispy Kreme, then you have high blood sugar, right? So insulin will take that extra blood sugar and force that glucose into your muscles and liver, where it's converted into glycogen. So glycogen is the storage form of glucose in animals. And like I said, it lasts about 2 to 3 days, and then your body converts it into fat. Now, if you happen to have a day where you don't have a lot of food to eat, then your body can break down this glycogen into glucose molecules, and that can help us build what? Energy, or ATP. Okay, so if you've been naughty and you've had a dozen donuts, then you have about 2 days to burn that glycogen off before it's stored as what? As fat. So your body gives you about a 2 to 3 day grace period for you to burn it back off, otherwise it's yours to keep. This is a picture of starch. You'll notice again these 6-sided rings are glucose molecules, and we don't actually make starch, but we can certainly enjoy eating it in food groups such as rice, whole grains, breads, potatoes. So, you know, these things that are white and taste good like potatoes and bread, these have lots of starch in them and pack a lot of energy. When your body eats, well, when you eat starch, you break this down into glucose molecules, and of course that can raise your blood sugar level. And if you raise your blood sugar level, then your body may end up storing this as glycogen. So if you eat too many starches, you can gain weight because your body can't burn off all those glucose molecules and instead will store them as glycogen. Now, this is another sugar. It's a polysaccharide called cellulose. You'll recognize it as a sugar because of its OSE ending. And again, it has glucose molecules as its foundation, but we lack an enzyme called cellulase that we cannot break down this particular type of polysaccharide. So what kinds of food groups are high in cellulose? Green leafy vegetables like spinach and lettuce are great sources. Corn has cellulose in it. those things that pass through your body undigested are classified as cellulose. So most of what your stool contains is insoluble fiber, fiber that you cannot digest, which is cellulose. By contrast, starch is a soluble fiber. You can break down starches, but you cannot break down cellulose. We just lack that enzyme called cellulase. Other animals do have cellulase. Cows have it, for instance, because they can break down the cell wall of certain plants that they eat. So if you eat cellulose, it makes your bowels move more quickly, and of course, they say that's good for bowel health because we don't want feces sitting in the digestive tract for any length of time. All right, just a closer look at those cellulose molecules, and they are found in plant cell walls. So corn, green leafy vegetables, spinach, lettuce, those kinds of things are great sources of cellulose molecules. So carbs come in many forms. On the left you see fruits, and these are oftentimes mono and disaccharides. They taste sweet to us. Starches taste less sweet, but starches pack a lot more energy that requires us to do a lot more work to burn them off. So if you were to do a marathon, which would you pick? An apple before your run or a complex carb like pasta? If you have the choice, a complex carb like pasta is going to give you a longer burn of energy than a simple sugar found in a fruit or vegetable. All right, so let's now turn our attention to our next organic compound group. These are the lipids. Lipids are known as the fats group, and they actually have two building blocks, fatty acids and glycerols. Alternately, the building block here is known as a triglyceride because there are 3 glycerols in each of these typical lipids. Lipids can store energy, they can insulate around organs, and they also perform a lot of other functions, such as behaving as sex hormones, for instance. Lipids get a bad reputation because they can clog our vessels, but they are very necessary for helping us build our cell membranes. So don't let them have a bad rap in your head. They actually do have a very important function in our body. Listed below are several types that we're going to talk about, especially the saturated and unsaturated fats, and the phospholipids and the steroids. So we know that lipids have 2 building blocks. They have a glycerol head and a fatty acid chain. They're called triglycerides because they typically have a set of multiple chains here, oftentimes 3. The glycerol head is polar. That's taking you way back, right? Polar heads have a hydrophilic region to them, while the fatty acid chains are nonpolar and they are hydrophobic. So these molecules get together and actually make your cell membranes. Here's 2 forms of the fatty acid chain. I'm going to ignore the portion here that I'm blocking off. Okay, I'm going to focus on this portion here that makes up the fatty acid chain. So going back, way back, you might recall carbon. Carbon had 6 electrons. So if carbon had 6 electrons, I'm just putting a C there for carbon, 2 of those electrons went on the innermost orbital, and how many go on the next orbital? 4. So that means that we do not meet the octet rule. We need 4 more electrons in order to satisfy that octet rule. Take a look at each of these carbons. Let's just pick on this one here. This carbon has 1, 2, 3, 4 single bonds. Each single bond, which is represented by a line, shares a pair of electrons. So in doing this, the carbon atom actually satisfies the octet rule because it shares an electron with hydrogen, the next door carbon, this hydrogen, and yet another carbon. So by sharing pairs of electrons, that carbon has stabilized its valence shell. So now we have a total of 8 electrons in the valence shell by doing this sharing. So when you see a saturated fat, you see all single bonds, you see carbons and hydrogens all bonded together, and you see a straight fatty acid chain. This straight fatty acid chain packs tightly on top of other straight fatty acid chains, causing no air in between these molecules, and this to become a solid at room temperature, something like butter, for instance. Okay, the unsaturated fatty acid chain down below, you'll notice has a double bond. How many pairs of electrons are shared in a double bond? That's 2 pairs of electrons. So why do this? Well, we're missing hydrogens that should have been sitting right here. And since there's no hydrogens, carbons have to turn to each other to form a double bond. That allows for us to complete the valence shell with 8 electrons and stabilize their outermost orbitals. So I'm going to erase these hydrogens down here. All right, and that means that when you see hydrogens missing from the fatty acid chain, that you have to double bond in order to satisfy the valence shell. Well, that causes a bend or a kink right there in that fatty acid chain. Now, that allows for air pockets to get in here, and these unsaturated fats then are liquid at room temperature. This is something like vegetable oil, canola oil, cottonseed oil. These are all oils because they are unsaturated. Now, this one happens to be a monounsaturated fatty acid chain because there is simply one double bond in that chain. So take a look at this unsaturated fat. Once again, I'm going to ignore everything over here that I'm blocking off. That's part of the glycerol heads that you see. What we're interested in are these fatty acid chains. Each one of them has several double bonds, like you see here. So this one would actually be a polyunsaturated fat because there are multiple double bonds in these fatty acid chains. In fact, this is a fatty acid chain here, and a second one, and a third one. Now, this should make sense why we call it a triglyceride. There's 3 fatty acid chains for this glycerol setup, and of course, each of these is an unsaturated fatty acid chain. So, what do you think? Should this be a liquid or a solid at room temperature? It should be a liquid at room temperature. Again, ignore what's over here. That's part of the glycerol heads. We're going to look at these 3 fatty acid chains, and they are all saturated. All right, how do you know that? There's no double bonds, and every carbon has hydrogens bound to it. So would this be liquid or solid at room temperature? This one's a solid, something like butter, lard. So unsaturated fats are considered to be good because they contain less hydrogens bound to their fatty acid chains. They're easier for our bodies to break down, and they cause less problems because of that. The saturated fats are those like butter, milk products, lard, things that tend to taste good but are awful for our bodies because they contain more hydrogen atoms bonded to the fatty acid chains and are more difficult for us to break down. So the more hydrogens you can pack to the fatty acid chain, the more work your body has to do to break down those molecules. So from left to right, let's take a look. We've got 3 examples of fatty acids here, and we've got a saturated fatty acid chain on the far left. How do we know this one is saturated? No double bonds, no kinks. Every carbon has hydrogens bound to it. There's none missing. So this one packs a lot of energy on the far left. How about the one on the far right? It's polyunsaturated. The reason for that is there's hydrogens missing, and every time there's a pair of hydrogens missing, those carbons double bond to each other. And the carbons double bond, creating a bend or a kink in this fatty acid chain. So there's several bends or kinks here that we're looking at. That would be your healthiest choice because it contains the least amount of hydrogens bonded to the fatty acid chain. This one in the middle is a monounsaturated fat. It has only a double bond there, a single double bond is what I'm wanting to say. And there's actually no, not a pair of hydrogens that you would normally have seen sitting there. So oleic would be better than steric, but not as great for you as linolenic acid. Here's a picture of a monoglyceride, and on the left, I'm going to circle your glycerol. And on the right, you see a saturated fatty acid chain. How do you know it's saturated? Well, it has carbons single bonded to hydrogens, and there are no hydrogens missing. So imagine when you read food labels, you see monoglycerides, you see diglycerides. Here's a set of 2 fatty acid chains for that glycerol head. And then you see triglycerides here, which is 3 fatty acid chains. Boy, if you see triglycerides on a food package, that's a lot of energy packed into that molecule. Each one of these fatty acid chains has to be broken down by your body. So if you had the choice, I would certainly pick a monoglyceride, and I would pick a unsaturated monoglyceride if I could. Picking a triglyceride on a food product means that there's a lot of energy packed into these molecules, and because these 3 chains are all saturated, means that's a lot of energy for your body to have to break down. Okay, so there you can see again those 3 fatty acid chains. That is the reason we call this molecule a triglyceride. So this is how your body stores fat in your fatty adipose cells, and your body will transport triglycerides through the bloodstream to those adipose cells. So if you happen to have a blood test done and you have high levels of triglycerides, it means that you have a lot of fat storage going on and potentially could have unhealthy issues such as cardiovascular disease arise. This is a special type of fat called a phospholipid. You can see, of course, phosphorus is the prefix here, and lipid. Okay, so it does in fact have a phosphate group right there. That's why we call this a phospholipid. And this happens to be a polar region, meaning there's unequal sharing of electrons. So this particular region has a slightly negative charge. There are 2 fatty acid chains. One of them happens to be saturated. The other one, there's my clue, is unsaturated. It does have a double bond there. So these phospholipids make up our plasma membrane structure. They are incredibly important to how our body works. So just another look at that phosphate in the head region, and there's looks like 2 legs here, one doing a kick, right? These 2 fatty acid chains are hydrophobic, while the head is hydrophilic. So if the heads are hydrophilic, all of these heads out here, that means they love water. And all these tails in here, they're hydrophobic, so that means they hate or they fear water. Okay, and then there's another layer of heads down here that you can see. So interesting setup what we've got here. We've got a set of heads and tails, water-loving heads, that means they are hydrophilic, and water-fearing tails, that means they're hydrophobic. And they actually hide here on the inside of your plasma membrane, forming a bilayer or 2 layers. Not going to mention a whole lot about these. These Isosanoids are a special group of lipids. I do want to mention, though, the steroids, because they don't look like any other lipid. In fact, they are made up of 4 fused carbon rings. I'm just going to put a number inside of each of those. Okay, and these steroids are very important to us because they are the basis for cholesterol and our sex hormones. So even though they don't necessarily fit the rule of having a glycerol head and fatty acid chains, they are classified as lipids because they are often hydrophobic. So testosterone, estrogen, estradiols, androsteroids, these are all classified in this category here of being lipids because of their setup, what you see here. So lipids come in many forms. They can be solid if they're saturated. They can be liquid if they're unsaturated. And of course, some of them are healthy and beneficial to us, and others are less so.